But for turbulent means the Reynolds number is larger than 2,300. Now things get complex. We use for when the temperature difference is small. We don't need, we use the term the Dieter-Bolte equation, and note that for the exponent of Prandtl number, for heating and cooling is not the exact same. And when the temperature difference is super large, for some fluids such as oil, its viscosity varies significantly at a different temperature, can vary between 100 to several thousand. Then we need to use equation 61 to add one modification factor to take account the thermal property variations on temperature. We need to use 8.61 with all thermal properties evaluated at average mean temperature. But look at the subscript S. That means for this viscosity, we need to use the value at surface temperature. It's very similar to what we have for external flow. And for turbulence entry region, because on Wednesday we know that thermal entry length is more or less like 10 diameter of the 10 of the tube diameter. If the tube is long enough, we can directly use what we have, the Nusselt number, the constant Nusselt number at the fully developed region as the average value over the entire length of the tube. But when the tube is small, we use equation 8.63, and this average value should be larger or smaller than our average. Then this constant value should be larger or smaller in the entry region. Larger, right? Because it decreases in entry region, they maintain constant. Then we use for the short tubes, define if the length is smaller than 60 diameters, we use equation 8.63. And all the above cases have an implicit assumption for Prandtl number larger than 0.7. But when we deal with molten liquid metals, it has very, very small Prandtl number. Can be as low as 0.003 to 0.05. Then we use 64 and 65 to calculate the local Nusselt number. They also tabulated for different surface thermal conditions. When we have non-circular tubes, I don't know where we can have some triangle tube surface or rectangle. Those for laminar flow in fully developed region, those constant Nusselt number can be directly checked from table 8.1. But we need to define for non-circular tubes, we need to use something named hydraulic diameter as an effective diameter to substitute in calculation of Nusselt number and Reynolds number. The subscript H, hydraulic diameter, defined as 4 times the cross-sectional area of the tube. It can be any shape. Over the P here is the weighted perimeter. By Wikipedia, the weighted perimeter is the total length, which is weight. Which is in contact of the fluid inside, right? And let's say if we have a circular tube, our cross-section area is just pi over 4 the square root diameter, and the weighted perimeter is pi over times product of pi diameter. So for circular tubes, the hydraulic diameter is simply its diameter, right? And that's for circular tubes. And it lists very, very different shapes for rectangle, for square, for triangle, and of course those constant are not the same for whether it is uniform heat flux or uniform surface temperature. Then we check this shape, locate where it is, and find the constant Nusselt number with this effective diameter. One common case is the concentric annulus, where the flow flows through the space between the inner surface and the outer surface. And of course, it's not a pure circular cross-sectional shape. For this annulus, we calculate its, we need to calculate the hydraulic diameter as the effective diameter for the correlations tabulated. The cross-sectional area is the difference between the outer surface minus and the inner surface. What is the weighted perimeter for this concentric annulus? So for the weighted diameter, it's a sum because it's in contact with the inner surface of outer diameter, and also get in touch with the inner diameter. So in this way, the effective diameter for annulus is the difference between outer diameter and the inner diameter. Here, there's a little bit tricky to calculate the weighted perimeter. It's a sum of both, not simply inner diameter or outer perimeter. And it's all tabulated. Table 8.2 gives for one surface is insulated, one is maintained as constant temperature, and one is insulated. And the table 8.3 gives us for both surfaces maintained as constant heat flux. But the methodology to deal with internal flow calculations is always the same. It's exactly very similar to what we have for external flows. The steps we need to follow is that first we need to select the correct formula to use for external flows. We locate for different geometries, whether it is flat, or cylinder, or sphere. But for internal flow, we need to know whether it is a circular tube or non-circular. For circular, it simply use the diameter of the tube. For non-circular, we use something called the hydraulic diameter, right? And then we calculate the Reynolds number to tell whether it is a laminar flow or turbulent flow, and the Nusselt number. Then based on the range of Reynolds number and the Prandtl number, we can use the correct formula to calculate the Nusselt number, then turn it into dimensional form, the convection coefficient.